This video is going to be about electrical resistance. It's kind of the last of the videos on DC circuit basics. So I would recommend having a quick look at the videos on current and potential difference before starting this one. So electrical resistance, what is it and how do we define it? Electrical resistance, as the name suggests, is a resistance. It's an opposition, if you like, to the flow of current. But it is essentially defined by this equation. It is the ratio of potential difference to current flow. And I will explain why. So if we think about a conductor, oh my goodness, that was a pretty weak straight line, but it's fixed it for me, thankfully. If I think about this is a section of wire that I'm considering with some sort of current flowing through it. If I could see into this wire, I would find that within it there are metal ions. I'm just going to draw them with gaps in between. Obviously that's not quite the reality, but just to illustrate, let's draw in a few ions like that. And interspersed in there as well, at least one for each ion generally, are free electrons, delocalized electrons, that are able to move. It is those delocalized electrons that will carry charge for us through this material. So, under normal circumstances at room temperature, these electrons would be moving with thermal energy and they would be bouncing off these atoms at a pretty furious rate, I hasten to add. They're not slow. At room temperature, electrons might be moving at 10 to the 5 meters per second. So they're colliding with atoms very, very frequently indeed. So they bounce about all over the place in random motion. There is no net velocity, there's no average velocity because the motion's random. So if I summed all of the velocities of the electrons in here, there would be as many electrons moving right as left, and I would get an average velocity of 0. If, however, there is a potential difference between the ends of this, and I'll just remind you what we mean, or rather where a potential difference comes about. A potential difference, I'm just going to shorten these because I kind of ran out of patience drawing. Oh, that's gone badly for me, hasn't it? I ran out of patience drawing the ions, and now my lines are too long. I don't know why it won't let me shorten this one though. I'll give up. If there's a potential difference between the ends of this conductor, that potential difference tells me that an electron at one end, for example the left end, has a larger potential energy than at the right end. And why? That is due to its proximity to other electrons. So if at this end I have a high concentration of electrons and at this end I have a low concentration of electrons, well, because this electron is closer to other negative charges than it would be when it's here, it has a different amount of potential energy. And that's what a potential difference is. So if I imagine having a potential difference between these locations in my circuit, that's fine. That is the reason that exists is because there will be a difference in concentration of positive and negative charge. What that means is if I just consider this electron, for example, or any electron that's in between these two locations, there will be a net force on that electron. It is being repelled from the high concentration of electrons on the right, and it's being attracted towards this low concentration because remember, in a neutral substance there would be one free electron for each positive ion, but if there's a lower concentration than that, then I've actually got a positively charged region. So every single electron in this wire is experiencing a net force to the right. And Newton's second law, F equals ma, says that resultant force equals mass times acceleration. Electrons have a tiny mass, so even with a relatively small force, they accelerate at a pretty high rate. So all of these electrons should be accelerating to the right. You'd be forgiven, therefore, for thinking that these electrons just get faster and faster and faster and faster as they move through the material, but they don't. And that is important. We'll come back to that concept in a moment. Why do they not just continually get faster? Well, because as they accelerate to the right, they collide with these ions, and then they accelerate again, collide, accelerate, collide, accelerate, collide. Those collisions that keep stopping them, keep slowing them down, and importantly, keep removing energy from them are the reason that they don't just continually get faster and faster. In fact, what I would find is that if I took the average speed of electrons here and compared it with the average speed here, or the average velocity, I should say, that I would get the same answer. The velocity here, the average velocity here, is the same as the average velocity here. And the reason for that is because each time these electrons accelerate, each time they speed up, they were going to collide with one of these ions. That has several effects. Those collisions with the ions transfer energy to the ions and cause the ions to vibrate. And the ions will, of course, already be vibrating at room temperature, but nevertheless, they'll cause additional vibration. That energy is ultimately dissipated as heat through the material. And that means that our electrons are losing energy every time they collide. If we stop to think about that for a moment, that checks out with the idea that their speed, their average speed, isn't changing. Because this potential difference, remember, is telling us a potential difference is a potential energy per unit of charge. So the fact that electrons are moving from here to here means that as they flow from one of these places to the other, their potential energy is changing. However, if their average velocity isn't changing, then their kinetic energy has not increased in that same movement. So where did that potential energy go? If they have lost potential energy but they haven't gained kinetic energy, we know that energy cannot be created or destroyed. So where has that energy gone? In this case, that energy has been transferred to these ions in the form of heat. So that's that. That is the nature of resistance. That's how it comes about. You could well imagine that if I consider different materials, that the amount of energy being lost in these electron collisions might be different. A different substance might have more massive ions, for example, or the nature of those ions may be different. So the way they're bonded together could be different. So the amount of energy loss that's happening as these electrons collide with them, the proportion of their energy that they transfer, could be different. And for that reason, different materials of the same dimension may well have different resistance. There's another thing worth remembering here. Temperature dependence is important too. The temperature dependence. And if we think about that, that's relatively easy to explain too. If I increase the temperature of this piece of wire, if I raise its temperature, the first thing I would notice is that the particles move faster. All of the particles move faster, and that includes these free electrons. So remember I said at room temperature they're moving very quickly, they're colliding with ions. If I increase the temperature, they move faster. And if they move faster, the number of collisions they have with ions per second increases. So an increase in temperature leads to a faster motion of electrons. That in turn means there are more collisions between electrons and ions per second, or a higher frequency. That's short for between electrons and ions per second. Now that per second bit is quite important. That means there is a higher rate at which the electrons are losing energy. But more collisions per second if I have the same current. So for the same current for a given current, I have the same amount of charge passing through the substance per second. Because remember, current is defined as the rate of flow of charge. So for a given current, if I have the same amount of charge passing per second, but it's losing more energy per second, that means each unit of charge is losing more energy to the ions as it passes through. So I could write that as greater energy loss, or greater energy transfer is a better phrase. The energy isn't lost, we know where it's gone. It's been turned into heat, it's been turned into vibrational energy in those ions. My handwriting's a bit ropey, sorry about that. A greater energy transfer per unit of charge. And this bit, energy transfer per unit of charge, let's just remind ourselves what potential energy is. And let's just go back to this diagram where I said, if I'm moving charge, and you can, again, it doesn't matter if you think about just a unit of charge moving or individual electrons. If I'm moving charge from one end to the other, there is no gain in kinetic energy for that charge. So the potential energy difference between the ends is equal to the energy loss, or the energy transfer per unit of charge. So this greater energy transfer per unit of charge means greater potential difference for a given I, for a given current. And therefore, if I go back up to my definition of resistance, given that we're defining resistance as the ratio of V to I, if I have greater potential difference for a given current, I have a greater resistance. So for most materials, if you increase their temperature, you increase their resistance. And that is why Ohm's law is very, very carefully phrased. I'll just state Ohm's law. I'm sure you're familiar with it. But Ohm's law, be careful when you're describing Ohm's law. V equals IR is not a good description of it. Ohm's law states that the potential difference across something, across a component, or an object, it doesn't really, anything that conducts, is proportional to current through it. At a constant temperature. Because that would not be the case if the temperature changed. And since the flow of charge, since current does transfer its energy typically as heat as it moves through a material, it's pretty common for the temperature of a conductor to change as you increase the current flow through it. But that is a conversation for another day. So I'll stop there.